Hey, going to look at a couple more examples of the first derivative test and intervals of increase and decrease, because I think my first lesson video went a little bit too fast. People seem to be having difficulty. So here's two more problems using this method. When you want to find where a function increases or decreases, you first have to find critical numbers. So we will take the derivative and set that equal to 0. And your zeros of the derivative are potential max and min values. So first we find critical numbers. I'm going to factor this. I do see that 3 goes into everything. So that gives me x squared minus 2x minus 15, which continues to factor 2x plus 3x minus 5. And I get critical numbers of -3 and positive 5. Those are zeros of the derivative. Now, if I'm going to determine where a function increases or decreases, you have to remember a function increases when the derivative is positive and decreases when the derivative is negative. So my function increases when f prime is positive. That means your slopes are positive. Your function increases. And your function decreases when slopes or f prime is less than 0. So that's kind of how we're going to have to think of this. So I like to do the number line. I like to plot my two critical numbers on a number line. Make sure you put them in order. -3 does come before 5. And since I'm trying to determine the signs of the derivative, I need to know when the slope is positive. I need to plug numbers into my derivative. So I'm going to pick some test points, pick something to the left of 3, like maybe 0, something between 3 and 5, and something after 5. And since I'm trying to determine the signs of my derivative, this number line represents the derivative. Now, if I plug in, that's supposed to be -3. That's going to change. See, now there's a potential mistake. Make sure you copy your critical numbers down, right? Because 0, my numbers are now 4 still works, but I would still like to plug 0. And I'm going to plug 0 in here and -4 in over here. Now, if I plug -3 into my derivative, and I like to plug in to my factored derivative. So I'm going to plug in right here. I'm going to plug in my test points to this. So plug test points here. And if I plug in -3 or 5, I get 0 for my derivative. So I like to put zeros there, letting me know that that's when the slope is 0. And then I'll plug in -4, and I'm going to plug into the derivative. F prime of -4 is going to be, let's see, -4 plus 3 is negative. -4 minus 5 is negative. And there's a positive 3 on the outside, so 2 negatives make a positive. So my derivative is positive to the left of -3. And then I'll plug in 0. F prime of 0 is going to be 0 plus 3, positive, 0 minus 5, negative, a positive times a negative. And then I'll plug in 6. F prime of 6 is going to be 6 plus 3 is positive. 6 minus 5 is positive. So positive there. And remember, this is my derivative. So if my derivative is positive, that means my function is going up. If my derivative is negative, that means my function is decreasing. I have negative slopes. If my derivative is positive, that means my function is increasing. We have positive slopes. So my intervals of increase and decrease, my function increases on the intervals -infinity to -3. That's where the positives ended. And then again from 5 to infinity. And then my function decreases on the interval -3 to 5. And I do like to use parentheses for your intervals of increase and decrease. So there's my interval of increase and decrease. Then to get my max and mins, let's see, I think if my function goes up, then it goes down, then -3 is going to be a local max. So I have a local max at x equals -3. And if I ask you for the y-coordinate, to get y-coordinates, you plug into the original function. I'm not going to do that just for the sake of time. Plus, that would be kind of ugly having to cube and combine like terms and stuff. Let's see a local min. Let's see if I have a local min. Well, if my function has a minimum, that means my function has to decrease and then increase. So my function decreases and then increases, and that change happens at 5. So I have a local minimum at x equals 5. And this right here is the first derivative test. When I use my intervals of increase and decrease to determine the location of local extremes, then that is the first derivative test. And that is what we're doing with this section. So critical numbers, do your number line, remember to plug into the derivative. The derivative is what tells you the slopes or when your function increases or decreases. Alright, let's try one more. What am I doing there? I wanted to see how long my recording is so far. 5 minutes, not too bad. Okay, let's do another one. Here I have y equals all of this mess. I will take the derivative, so my derivative, y prime, or you could say dy dx, this is a quotient. I'm going to have to do quotient rule. So low d high minus high d low, which is just 1, all over low low. And then we clean that up. So my derivative, let's see, I'm going to distribute my 2x. So 2x squared minus 4x minus x squared over x minus 2 squared, which ends up being simply x squared minus 4x over x minus 2 squared. So I do my quotient rule to get my derivative. Now I take that derivative and I will set it equal to 0 to find my critical numbers. Okay, well, if you have a fraction, if you want a fraction to equal 0, that means the numerator needs to equal 0. So I will factor an x out of my numerator. X times x minus 4 equals 0. I get critical numbers of 0 and 4. So that's when my derivative is equal to 0. But we also need to be aware of what's happening in the denominator. Denominators are important because if you remember in math, or in life in general, I guess, you cannot divide by 0. And I'm looking at my derivative here, and if x equals 2, I run into a problem. So I'm just kind of thinking over here, if x equals 2, my derivative does not exist, right? So f prime of 2 does not exist, which now we need to investigate that a little bit more. Since that does not exist, I need to look at my original function, and it turns out I cannot plug in 2 to my function either. And actually, this is something that we probably need to look for at the beginning of the problem. If your denominator equals 0, and it doesn't cancel, then that means we have a vertical asymptote at 2. So even though my derivative does not exist, it's not a critical number, because critical numbers are only when your derivative does not exist or equals 0, and you can plug it into the function. Since 2 does not work in my function, then I can't consider 2 a critical number. So by name, it's not a critical number, but the weird part is, when you do your number line, you're definitely going to put your critical numbers, which are 0 and 4. I'm also going to put 2. Even though we don't call it a critical number, it's still a special value. It's something we need to think about. And I'm going to make a little note to myself that 2 is a vertical asymptote. 0 and 4, if I plug those into my derivative, I get 0. So I have my critical numbers of 0 and 4. My vertical asymptote is still part of my number line. It's something we need to consider. And then we pick test points. So I'll plug in -1, +1, +3, and +5. And I like to plug into my factored or my cleaned up derivative. Let's see. So here is my derivative. Here's my derivative, and I'm going to plug numbers into that. So if I plug in -1, -1 squared is 1, minus 4 times -1, that will be 5. That's a positive. So my numerator is positive. My bottom is being squared. So my bottom is always going to be positive, right, regardless of what I plug in. So if I plug in -1, I get a positive over a positive. which is overall a positive. So let's plug in 1. 1 squared minus 4 times 1. That is a negative on top. I'll plug in 1 to the bottom, I get a positive. A negative over a positive is a negative. If I plug in 3, 3 squared is 9, minus 4 times 3, that would be a negative. My bottom is positive. So that gives me a negative. And then if I plug in 5, 5 squared is 25, 5 times 4 is 20. Subtract that, you get a positive. 5 minus 2 squared is going to be positive. So there's my number line. And then from that, we can find our intervals of increase and decrease. So I know that my function increases on the intervals negative infinity to 0. And then again from 4 to infinity. Your function increases when the derivative is positive. We plug numbers into the derivative. My function decreases from 0 to 2, and then again from 2 to 4. You cannot go straight from 0 to 4 because your function does not exist at 2. We have to break this up. So my function decreases from 0 to 2, and then again from 2 to 4, and it's split up by vertical asymptote. And that's why you need to put that on the number line, because if you only plotted the critical numbers 0 and 4, then you're going to miss the fact that 2 is a vertical asymptote. You're probably going to just do the interval straight from 0 to 4. So make sure that on the number line you put your critical numbers and any discontinuities. So you put critical numbers and discontinuities for the function on the number line, and then we'll plug in numbers to the derivative and determine where the function increases or decreases. Hopefully this clears up a little bit of that mess of the video that I posted the other day. So there we go, and good luck.